Ask and you shall receive. You guys said that you were a little confused on angular momentum. So, let's go through some of the homework problems. I have pushed back the due date for your homework, giving you an additional day so that you have some time to figure it all out. I don't want your homework until you understand the problems. If that means the homework is late, for you guys, that's what I want. I'd rather have it late but done correctly than on time and you had absolutely no idea what was going on. So, here are all of the important equation-y things for angular momentum problems. And page 216 in your book has the big old table of moments of inertia. So, your homework started on page 285, number 30 to 35, then 65, 67, then 75. Let's start with number 30, shall we? All right, page 285. Here it is. What is the angular momentum of the moon around the Earth? Okay, what is the angular momentum of the moon around the Earth? Okay, well, angular momentum is moment of inertia times angular velocity. I want the moment of inertia of the moon around the Earth, and I want the angular velocity of the moon around the Earth. Alright, well, okay, if I have the Earth, and I got moon. Oh, hey, look, it has a circular orbit. It is a point mass at a distance away from an object. So this has a moment of inertia given on page 216. Let's see. Didn't see it. Where did it go? Let's see. Here we go. Cylindrical hoop about its center. Or a point mass about its center. I need to know the mass of the moon and the distance between the center of the Earth, the center of its orbit, and the moon. Squared. Okay, that's easy enough. Now, angular velocity. Huh. Oh, wait. Angular velocity. We know angular velocity. That's going to be the period, how long it takes to make one entire revolution, divided by 360 degrees, the amount of degrees it takes to make one complete revolution. So I also know that that is going to be the period over 360 degrees. Alright, so I need to know the mass of the moon, I need to know the distance between the moon and the Earth, and I need to know the period of the moon. Alright, well, let's finish reading the problem, shall we? The moon's mass is... Oh, hey, what do you know? They're giving it to us. The moon's mass is 7.4 times 10 to the 22nd kilograms. And it orbits around the Earth at a distance of 3.8 times 10 to the 8 meters. We're in kilograms, we're in meters, we're in the units we want. So we can find the moment of inertia of the moon about the Earth. The hard part now is figuring out the angular velocity. Alright? Well, how the heck are we going to do that? How long does it take the moon to go all the way around the Earth? I don't know. I'm going to use this magic thing called Google. And Google is going to tell me what's going on. Let's see. Period. Moon. Around. Earth. Alright, so apparently it's 27.3 days. Huh, but Well, okay, that's .phys.utk.edu. University of Tennessee. Okay, that's probably pretty reasonable. The moon takes 29.5 days to return to the same point on the celestial sphere as reference to the sun. It reflects corresponding orbital of 27.3 days. Ooh, okay. There's more than one thing going on here. So I'm going to open that. Ooh, an orbit of the moon on Wikipedia. That's probably fairly safe. I'll check out that too. Alright, the moon appears to move completely around the celestial sphere once in about 27.3 days as observed from Earth. Alright, done. That's all I want. There is other stuff going on, but we do not care. We only care about our frame of reference. And our frame of reference is 27.3 days. Alright? Except I don't want it in days, do I? I want it in seconds. Oh, goody. Alright, so, let's see. Days. I know that one day is 24 hours. And I know that 1 hour is 60 minutes. And I know that 1 minute is 60 seconds. So I can find out how many seconds there are in the lunar period. 27.3 times 24 times 60 equals 2.36 times 10 to the 6 seconds. All right. Plug them in, get an answer. I'm not going to go over it from here. At this point, you should be able to do it. 31. A little girl is going on the merry-go-round for the first time and wants her 47-kilogram mother to stand next to her on the ride, 2.6 meters from the merry-go-round center. If her mother's speed is 4.2 meters per second when the ride is in motion, what is her angular momentum around the center of the merry-go-round? Alright, so let's write down what we know. We know that it has a linear velocity of 4.2 meters per second. We know that she has a mass of 47 kilograms. We know that the distance from the axis of rotation to the person is 2.6 meters. All right. And what do we want? Angular momentum, which is moment inertia times angular velocity. Well, again, we have enough to find the moment of inertia. That's going to be m times r squared. In this case, because what we have is a point mass orbiting around a axis. The hard thing is, I got this, and I want this. Luckily, v equals c over t, c is 2 pi r. Alright, so if I know the velocity, and I know the circumference, I can find the period, and once I know the period, I can find the angular velocity. Alright, so that means, let's see, v is going to be 2 pi r over t, where t is omega theta, and I want to solve for omega, which is going to give me v times theta divided by 2 pi r. Alright, so that's going to be 4.2 times 360 degrees divided by 2 times pi times a radius of 2.6 meters. I'm just playing with parentheses to make sure that the calculator understands what I'm asking of it. And I get 92.6 degrees per second as my angular velocity. Alright, at this point, It's just an algebra problem. Numbers, plug them in, get an answer. Bam, bam, ba-bam, bam, bam. Next. 32. What is the angular momentum about the axle of the 500-gram rotating bar? Okay. Mass. 500 grams. So 0.5 kilograms. Angular momentum of the bar. All right. So what we have is we have 120 revolutions per minute. I'll talk about what the heck that means in a moment. We have a total length of 2 meters, and the axle appears to be in the dead center. So we have axle, 1 meter, 1 meter. We got the total mass, we got the distance from here to the outermost bit. All right, we have RPM. And I want angular momentum. All right, this is not a point mass rotating around an axis, so I'm going to check my data table on page 216. Let's see, a thin rod about its center. Hey, that's the first one. The moment of inertia in this case is given by 1/12 m, the total length, squared. All right. Well, we happen to know all of those things. Notice I put 4 because 2 squared is 4, 1 and 1 is 2. All right, I just need omega again. I need to know my angular velocity. I know that it makes 120 revolutions per minute. All right, so let's talk about what that means. 120 revolutions, where a revolution is 360 degrees, per minute. Oh, look. It's just a math problem. 120, an arithmetic problem, I should say, times 360 equals bam, divided by 60 equals bam. Done. Multiply, get an answer. All right, so I'm going to skip 33, 34, and 35. I'm going to do 65, and that's going to be the last one that I will go over for you guys. Actually, I want to do the hard one. Yeah, I'll do 75. Disc A, with a mass of 2 kilograms and a radius of 40 centimeters. Wait. Haha! And a radius of 40 centimeters. Rotates clockwise around a frictionless axle at 30 revolutions a second. Okay. We have disc B, also 2 kilograms, but this has a radius of 20 centimeters. Rotates counterclockwise. Also at 30 revolutions per second. They then collide in such a way that they stick together. well, this sounds like a conservation of momentum problem. I need to find the angular momentum of thing A and the angular momentum of thing B and add them up to find the total momentum before the crash. That must equal the total momentum after the crash. Let me write that again. And I know that the total momentum after the crash is going to be that. So as long as I solve for the moment of inertia of two things stuck together, I can solve for what I'm asked for, the angular velocity. All right, but first I need to find the moment of inertia of A and the angular velocity of A, the moment of inertia of B, and the angular velocity of B. Okay. Let's do this. This is a disk. I'm going to check my table. A cylinder or disk about the center. I equals 1/2 mr squared. 1/2 mr squared times 30 revolutions per second. Ugh. All right, well, let's see. 30 revolutions. That's 30 revolutions where each revolution is 360 degrees. Okay, so that gives me 10800 degrees per second. Let me write this a little neater. Angular momentum of B. Okay, well, that's still 1/2 mr squared, and it's going the same speed. With one major difference. This is going counterclockwise. This is going clockwise. Clockwise we have previously defined as the negative direction. All right. Let's add these things up. 1/2 times 2. I'm not going to worry about it. So I got 0.4 squared times negative 10800, which gives me negative 1728 momentums. And I get 0.2 squared times positive 10800, which gives me positive 432 momentums. The sum of these is negative 1296. All right, that is the angular momentum before the collision. 1296. What's the moment of inertia? Well, the moment of inertia is going to be a moment of inertia A plus moment of inertia B. You just add them up. It's crazy. It's brilliant. It's calculus. So, I get negative 1296 equals 1/2 times 2 times 0.4 squared plus 1/2 times 2 times 0.2 squared times omega. Solve for omega. All right, well, I'm just going to cancel these out to make things a little easier on us. Omega is going to be equal to negative 1296 divided by 0.4 squared plus 0.2 squared, which is 0.4. 4 squared plus 0.2 squared, negative 6,480 degrees per second in the negative direction, or clockwise. Which makes sense, because although they're going at the same speed, the thing going in the clockwise direction is bigger. And I don't mean heavier, I mean bigger, larger. Since it is larger, but going at the same speed, it must have more angular momentum. Alright, so there we go. Help on angular momentum. Finish your homework.